Okay, can you guys see my screen?
Yeah.
Okay. Okay, before we've been kind of talking about acid and bases for a while, and how we basically define acids, and we're going to kind of define it a little bit further in that sense. We always said that acids are going to be proton donors. There's a guy named Arrhenius. Arrhenius basically had defined acids as just things that basically had the H+ ion, okay? And then, or the hydronium ion, or the hydrogen ion. And then a base will be defined as something that had the hydroxide ion, okay? And this was Arrhenius. It's a very simple view of looking at it. It was very limited in terms of the scope. And so he basically came up with the equation. Thank you, Selena. I'll put that on there. That's actually a good idea. He came up with the equation that HA, where H is representing the hydrogen ion, A represents either a polyatomic ion, a polyatomic anion, or an anion. And then when you get the separation, you'll get your hydrogen ion, and you'll get your polyatomic ion or your anion. Now, this dissociation has always been as thought of as being complete. So hence the arrow is only going in the forward direction. Arrhenius also defined his base the same way, right? So strong bases also dissociates completely. So you end up with your metal ion, and then you end up with the hydroxide ion. So have you guys ever smelt acetic acid or vinegar? Or I know we tasted vinegar. What does vinegar taste like?
Sour, like lemon.
Sour.
Like lemon and salt, kind of.
Yeah. So it tastes sour, right? And then we know that lemon, the reason why lemon is sour is because it has citric acid, right? So both cases, we know that it's acids in general are very sour and tasty for the ones that we are capable of tasting. And if you ever took a big whiff of an acid, even though you're not supposed to take that whiff, you know how you're supposed to, use your hand to sit there and go over the bottle to get the fumes. Most people, the first thing that they do, they stick their nose right over something and they take a big whiff. Everybody I know has done that at some point with a bad acid. Then they burn the crap out of their nose, right? But even in that context, you smell that sourness from hydrochloric acid or phosphoric acid, okay? So even those acids are also having a very sour smell to them, or a sour stench to them, as it burns the crap out of your nose and damages. Okay? So we've gotten to the habit that we can actually determine the pH of the acid. And the way that we've been able to do that is by litmus paper or pH paper. And those pH paper basically have dyes. These dyes have been basically isolated, and a lot of these dyes come from plants and stuff like that, and we get color changes as a result of that. So, and you guys have bbeen doing that in the lab since the very beginning. You've used pH paper since the start, right? We can also use potentiometric measurements, or potentiometers, or pH meters, right? So to sit there and calculate the amount of positive ions that are in our solutions, right? Or positive hydroxide, the hydronium ion. Okay, so now we're going to kind of expand that definition of Arrhenius to more broadly. And I've been kind of teaching you guys that from the very beginning, because we didn't even talk about Arrhenius's way. We kind of assumed that Arrhenius' way would fall under Brønsted-Lowry's method. Brønsted-Lowry basically says that the way that you define an acid is going to be a proton donor. If we think about a proton, and we also think about the H+ ion, we know that an H plus ion has how many electrons?
0.
Okay. How many protons?
It would have 1.
And how many neutrons?
1.
Does it have 1?
Usually 0.
Yeah.
Okay, so what are we really donating if we add a hydrogen ion to anything? What's left? I mean, an atom is only made up of protons, neutrons, and electrons. So what's left in this case?
Just the proton.
Just a proton. So you're donating just the proton. So now you see why it's called a proton donor?
Yes.
Okay, I need engagement. Okay, so a base is considered to be a proton acceptor. Okay, so an acid is going to be the proton donor, and the base is going to be a proton acceptor. So the acid is going to be giving away the proton, or giving away the hydronium ion, or the hydrogen ion, and the base is going to be accepting the hydrogen. Okay. So the other thing about Brønsted-Lowry's theory, it says that, you know, although you could have bases that favor one side or the other, but acid and bases, they form some type of equilibrium, right? So meaning that before we were just looking at the reaction going in the forward direction. Now the reaction can actually form an equilibrium. It can go both the forward direction and the reverse direction. Okay, so for example, here we have ammonia and water. Okay, so here ammonia is going to be acting as the base, and water is going to be acting as the acid, because when these guys react, you get the ammonium ion where it's received from water. Oops. It received that H plus. Okay, and as a result of that, we're going to get the ammonium and the hydroxide. Okay, so we also get back what we call the conjugate acid and the conjugate base. The conjugate acid is that acid that is formed by the reception of the hydronium ion from the base. And then the conjugate base is the base that is formed by giving up the hydrogen ion. Okay, you guys see that? Yes, no, maybe?
Yes.
Mhm.
Yeah.
Okay, so here are a couple of chemical equations. And what I'd like you guys to do is tell me the conjugate acid and the conjugate base. And sorry, the acid and the base. So for A, what is going to be the acid? What is this guy here?
Nitric acid?
Nitric acid. Okay, so which one is going to be the acid, nitric acid or water?
The nitric acid.
Okay,
I was about to call it hydrogen nitrate. I forgot.
okay, and then water is going to be,
The base.
okay, so then the conjugate acid is going to be,
It's a trick question.
Is that going to be the conjugate acid? The H3O plus
Yep.
1?
conjugate acid is going to be,
But I thought that there were no conjugate acid or bases if there is an equilibrium. If it's just a one-way arrow.
oh, you're technically right. Since it is a one-way arrow, there wouldn't be a conjugate acid because it's not able to go back in the direction.
Mm,
Generically, this would be the conjugate arrow conjugate base if there was equilibrium form. So if there
Right.
was a diluted version of it, you could. So. You're taking it literally, yes. Okay, what about, so then that would be our conjugate base in that theory. If we had a weak and so really, in terms of a strong acid, so it kind of depends on the concentration. The more concentrated you are, right, the more probability that you're going to have at least a little bit of things going back in the other direction.
right. Makes sense.
Okay, now what about B?
Is that cyanide? CN?
That is cyanide.
Would that be the base?
Okay,
And water would be the acid this time?
that is correct. So the conjugate acid would be, oops,
The I don't remember what that's called. HCN.
so if it was called cyanide, the acid would be called
Cyanic. It just ended in IC, right?
cyanic acid. Yep.
Okay.
Okay, and the
And then
base would be
yeah, OH would be the conjugate base.
okay. What about actually it would be hydrocyanic acid according to the rule.
Oh yeah, because hydro means without oxygen, right?
Okay, what about the next one? Sulfuric acid and chloride ion.
Sulfuric acid would be the acid,
Okay, I would hope so since it ends with acid. Then the base would
right?
be
I don't know. What chloride? Is it just? I don't remember the naming convention.
chloride ion. Okay, now what about the conjugate acid and the conjugate base?
Wouldn't the hydrochloric acid be the conjugate acid?
That's right. And then the conjugate base,
The sulfuric? Or is it
hydrogen sulfate.
oh, hydrogen sulfate, yeah.
Come on, you guys are getting rusty with that nomenclature.
It's been a while.
So you know I'm gonna have to put one of those on the exam that you guys are gonna be getting next week. Your take home.
Wait, are you gonna post that online or do we have to go pick it up?
I'm gonna post it on.
Oh, okay.
I'm gonna have to pick it up. Okay, hydrogen sulfate ion and the hydroxide ion. Which one is the acid and which one is the base?
Would the hydrogen sulfate be the base and the hydroxide be the acid? Or no, it's vice versa, huh?
Yep.
The sulfate would be the acid and the hydroxide. I always forget hydroxide is usually a base.
The hydrogen sulfide is the acid because, like you can tell from the equation, it's losing a hydrogen, right? So it's donating.
That is correct.
Okay.
That's right. So the conjugate acid is going to be
Would it be sulfate?
Is that the conjugate acid?
Yeah, that's my educated guess.
Okay, that would be incorrect.
So it would be the H2O because it's gaining the hydrogen.
Okay, yes, so now it has that extra hydrogen. Now, if you go back the other way, it's going to be losing. So then that's going to be our acid. And then this is going to be our conjugate base. A real quick way of remembering, for me, a real quick way of remembering is that if this guy, that root there is an acid over here, then that root here is going to be the base on the other side. So it kind of balances out. You see what
I
I'm saying?
remember acids lose hydrogen and bases gain. So I try to like look at, which one is losing versus gaining.
Okay, so E. So we have the oxide ion and water,
Oh,
and it's going to
well,
make two.
water would be the acid on the left, right?
Okay,
So oxygen would be the base.
okay. Okay, what about on the other side?
I mean, is it just both?
That's right. It's actually going to be both. So this guy is going to be Ca and Cv. Okay, because in the case of water, O2 minus, we have this guy being donated here. So we're going to end up with OH minus for this, and then we're going to end up with OH minus for this, where the one that came this way would be now the acid, the conjugate acid, and this guy would be the conjugate base. So both. Okay, what about F?
I really hope you don't expect
Call
us
that a
to name these.
trihydrate?
Which one?
Would we call that a trihydrate?
That would be, so it would be copper. Yes, it would be the copper 2 plus trihydrate, yes. Or the tetrahydrate, tetrahydro copper ion. This is a complex ion. We haven't talked about complex ion yet. We'll get there. So you're saying this would be the acid or the base?
I think that the copper ion on the left would be the acid, but I'm only guessing that because it has the OH in it, and most acids have OH, right?
I would disagree with you.
Okay, well, I'm
That
not
would
sure
be the
then.
base because it has the OH.
Yeah, this guy is going to be the base. So think about what's happening. Okay, if you look over here and look over here, so then in this case, you're removing one H plus, and it's being delivered to here, right? So this is the acid is the proton donor. And then as a result of that, you're going to get your Al H2O 5 OH. So this is going to be your acid. And so this guy is going to be my conjugate acid, because now it had that extra H plus, making it complete. So then that's a conjugate acid. And then this guy is going to be your conjugate base. Can you see that?
Yeah.
Okay, what about this last one?
So,
Is that sulfuric acid, H2S?
Yep.
So that's the acid then.
It's hydrosulfuric acid.
Oh,
So you said
I'm
acid.
scared to say it because I don't remember any of the names anymore.
Okay, and then so then that's the base. So then what is the acid? The conjugate acid.
the conjugate acid would be ammonia.
And then the
Hydrogen sulfide would be the conjugate base.
okay, piece of cake.
Kinda.
Okay. So autoionization of water. So basically, when you stick water, let's say water in a glass or anything like that, it basically auto-ionizes. So what that basically means is that you're going to have small amounts of ions of the hydrogen ion as well as the hydroxide ion. And it's always going to be the same because water, it gets into equilibrium with itself. It's always going to be, if you have water that is appropriate and it doesn't have any contaminants, then you're always going to have a concentration of 1 times 10 to the minus 7 molar hydrogen ion and 1 times 10 to the minus 7 molar of the hydroxide ion. Okay, so if we take a look at that, 1 times 10 to the 7 times 1 times 10 to the 7 is going to equal our equilibrium constant for water, which is always going to be 10 to the minus 14. Okay, so when water is at equilibrium, which it's pretty much that way instantly, it's always going to be 10 to the minus 14th is going to be our equilibrium constant, and the concentration of each one is going to be 1 times 10 to the minus 7. Simple.
Yeah. This is where the pH scale comes from, right? Because it goes up to 14.
Exactly. Yes, that's exactly. So that's exactly where the acid base scale comes from. Is based upon water. So we know that neutral, pH 7, is water. Water is neutral. The reason why it's considered to be neutral is because pH is defined as minus the log base 10 of the concentration of the hydrogen ion, or we call it hydronium. Okay, you'll see it called that way a lot. Okay, so in this case, we know that the concentration of H plus is going to be minus log of 10 to the minus 7, which equals 7. Make sense?
Mm-hmm.
Okay. So again, it's based upon, the scale is based upon the water or the water equilibrium constant being 14. So the highest it can be is 14, the lowest it can be is 0. Okay. Although we can get negative values because of other things, but we'll talk about that here in a minute. Okay. Are you guys clear on this? You ready to move on?
Yeah.
I know a lot of words to say a little bit of stuff. Okay, so water is considered to be amphiprotic or amphoteric. The reason why it's called amphiprotic or amphoteric is because water could either be an acid or it could be a base. So water can act either way. So water basically swings both ways. Okay.
Would that apply to like baking soda too?
Yes, baking soda can actually act as an acid under certain circumstance and act as a base as well. So yes, baking soda can do that as well because it can donate that extra hydrogen that it has, or it could take on another hydrogen and form carbonic acid and make it to CO2 and water.
Can't you like essentially make anything act as both by just adding something that's like extremely opposite to it on the pH or whatever? Like something that would normally be an acid, you could be a base if you added something even more acidic, right?
For the most part, that's the case. In some cases, you can, right? So, like for instance, you have the chlorine ion, right? That's a base. You can't sit there and make it an acid.
Right. Yeah. Right. That makes sense.
Yeah, but there are other molecules that you could do that with. Okay, so we were talking about the pH. So we know that the pH is going to be equal to the minus log. This is the hydronium ion. It means the same thing as that H+. They're identical, essentially. The only thing the hydronium ion takes into account that the hydrogen ion has bound to water physically because it likes to bind to stuff. Okay, or bond to stuff. Now, the hydroxide, the POH, is going to be minus the log concentration of the hydroxide ion. Together, they both should add up to 14. pH and POH is going to always equal 14. And you're always going to use this scale for your definitions, okay? So we know that acids, all acids are going to be pH less than 7. So 6.99 and below is going to be an acid. A base is going to be anything that's going to be above 7. So 7.01 and above is going to be considered basic. Strong acids are going to have negative pH values. Okay. Piece of cake, go for it. You're ready to test it out? Okay, calculate the pH for 0.220 molar. Did somebody want to ask something? Are you guys there?
Yeah.
Yeah.
Okay. I thought I lost everyone because I kept hearing cake, cake. Or maybe that's just in my head because I want cake.
It's your body trying to send you a message that you're hungry.
That's right. Okay, so calculate the pH for 0.22 molar HCl solution. HCl is a strong acid with complete dissociation. So what would I do?
Do we start by writing the dissociation equation?
All we need to do is calculate the pH. So
Oh, did you just say the
calculate
negative
pH?
log of that number?
That's right. So we'll take
Oh.
pH is equal to minus log, because the concentration of your H plus is going to be the same concentration that you have for your your hydronium ion. So it's minus log.
So if you had something like H2SO4, then you would have to divide it by 2 or whatever.
Yes. And usually what happens is that you will have a double dissociation because you lose that first H and then you'll use the second H. We're going to talk about that Those are polyprotic acids.
Oh,
So
okay.
they're kind of special. Okay, so then
Right.
what do you guys get?
I got 0.6576.
0.657. 3 sig figs.
Yeah. So we'll actually round up to 8 then. It's
Okay.
only 3.
Okay, calculate the pOH for 0.100 sodium hydroxide.
So wouldn't you just take the negative log of that number?
Okay.
You just need the concentration of the hydroxide. And it's all the
Okay.
same.
That's right. Oops.
And for
That's
that one,
just
I got
1.
1. Yeah.
Okay, calculate the pOH for 1.80 molar HNO3. HNO3 is a strong acid with complete dissociation. So how would we calculate the pOH?
Would you divide that number by 3 first?
Why would we divide it by 3?
Oh, wait, no, that's just 3 oxygen.
So we would calculate the pH by taking the negative log of 1.8 and then subtract that from 14, because together
is
they have to
correct.
equal 14.
Okay, so that's going to equal give us a nice negative value.
Yeah, I got negative 2.55 or 0.255.
Oops. So then we take that number and we get pOH is equal to 14 minus pH. So then we'll get,
And then since it's
equals-
negative, wouldn't you get over 14?
that is correct.
Hmm.
Oops. .3. Okay, if we wanted to calculate the pH
Wait,
for a
I had a
0.
question. So why didn't we subtract 1 from 14 on B?
Because here we're able to calculate the pOH. So the pOH is just the log of the hydroxide ion, right? Here we're calculating the pOH for an acid. So in this case, all we're getting is the concentration of the H plus, right? And so we have to use that subtraction to figure out how much OH is going to be in there.
Okay.
Does that make sense?
Yeah.
Okay, what about the next one? Calculate the pH for 0.400 molar of KOH solution. Potassium hydroxide solution.
Is it basically the same thing where we do the negative log of 0.4 and then subtract it from 14?
Yep, so we have POH is going to equal negative log of 0.400. Now it's going to equal 0.398. And then we'll go pH. It's going to equal 14 minus POH. So that's going to equal 14 minus 0.398. So that's going to equal, what is that, 13.6. 13.6.
Yeah, that's what I got too.
Okay. Calculate the hydrogen ion concentration for a solution with a pH of 7.4.
Do we subtract that from 14 to start?
Okay. Well, we don't have to because we're trying to calculate the concentration of the hydrogen ion. So we know that the definition of pH is equal to minus log the concentration of H plus.
So you have to do
So-
the inverse of the log, which would be to raise both sides or put both sides in the exponent of 10. I don't know if that makes sense, but
Yep. So we'll have 7.4 to the negative 10 power is going to equal, if we go log concentration X to the 10th power. So these guys are going to kind of cancel each other out. And so then we're going to get a concentration of X plus is just going to equal 10 to the minus 7.4. And so if you put that in,
I got 3.98 times 10 to the negative 8.
okay.
is there any reason why they used log for this instead of just ln? Because I feel like ln is super common in chemistry.
It is. I don't know why they decided to do that. It predates me. I think because base 10 is a lot easier to work with than ln, you know?
Yeah.
And log is base 10, so
Yeah.
okay. Calculate the hydroxide concentration for a solution with a pH of 11.2. So pH is equal to 11.2. And we want hydroxide.
Don't you have to subtract that from 14?
That's right.
Well, 14 minus 11.2.
14 minus 11.2. And that's going to equal our
POH.
POH.
Which is 2.8. And then you would just plug that in as the same thing as like E.
Okay. So we have 10 to the minus 2.8. Equals 10 log concentration of OH. So concentration of OH equals,
You got 0.002.
I got 1.58 times 10 to the negative third.
Wait,
Oh, wait.
what?
Yeah.
10 raised to the negative 2.8 power, right?
yep,
Yeah.
I don't know. I tried it again. I still got the same thing.
You got, what did you get again?
I got 0.0015, but I just rounded it to 0.002.
I got 0.061.
I got 1.58 times 10 to the negative 3. Oh, I guess it's the same thing.
yeah, you just rounded too
Oh,
much.
I see.
Yeah,
Okay.
just this
Yeah,
one's a
just
scientific
notation.
Yep.
So we want to write it that way, so we have more like actual numbers, I suppose.
Yeah.
This looks neater. Yeah.
Okay, piece of cake.
Actually, I kind of have a problem with C, and so like to solve C, we had to say that pH plus POH is equal to 14, right?
That's
But
right.
then we immediately disprove that by getting POH equal to 14.3. It's just
Yeah.
weird. I don't like
It's off
it.
the scale. So it doesn't, so remember, you could have a negative value for your POH, right? I mean, your
Yeah.
pH. So which
It
also
just feels
means
like
that
we
you could,
shouldn't be able to use that fact and then right
Yeah.
away it like is something different. I don't know.
yeah. Gotta be flexible though, right?
I swear, the more time in chemistry, I just like you learn all the basic rules in general or introduction, and then like you just learn all the exceptions to those rules further down.
That's
Yeah.
right. That's right. That's
Honestly.
essentially what it is. Yeah. Okay. Okay, so when we talk about relative strengths of acids, so we kind of break up acids into subgroups, strong and weak. And we've kind of talked about that strong. A strong acid or bases, and bases, they go to 100% ionization, or they almost completely dissociate, right? And we've kind of talked about the ones that do that. We have them sort of memorized, right? So we have the 7 strong acids. So we have nitric acid, sulfuric acid, hydrochloric acid, hydrobromic acid, hydroiodonic acid, and your chloric acids, perchloric and chloric. So typically things that are per are going to be quick to dissociate, right? So they're going to do complete dissociation. Things that are ick are going to dissociate. except for when they're carbon-based acids. Carbon-based acids are going to be really, really weak acids, okay? And they're always going to partially dissociate. Strong bases, such as those in the group 1, are all strong bases. And then you have anything with the hydroxides with calcium, strontium, barium. So group 1 and most of group 2 are strong bases. Okay. Then the other ones are going to be assumed to be weak. Okay.
Okay.
Okay. So when we work with acids and bases, we write our equilibrium constants. So this is the equilibrium constant for weak acids. So we call it Ka. And that's just going to be the concentration of the hydronium ion times the concentration of the conjugate base divided by the concentration of the acid. We don't take in consideration water because water is a liquid, and so we don't take that in consideration when we calculate our equilibrium constants. Now, a weak base equilibrium, we're going to be using Kb. Kb is going to work the same way. It's going to be, again, if we look at in terms of equilibrium constants, it's going to be our products over our reactant. And that's the same thing that was up here. We had our products over our reactant. Question?
Is that the same Kb from the colligative properties equation where your delta T equals Kb times
No.
moles volume?
No. So that's the Kb for boiling point.
Okay.
Yeah. And so don't get those mixed up.
Even though they're exactly the same, but I'll try not to.
Yeah, see, and that's the thing about chemistry as well. We start running out of letters and we start renaming things, right? And it kind of throws us off. You got to think about what the question is asking us.
Right. Context clues.
Yeah. Okay. Oops. I carried away. So Kb in terms of Ka. So when we have an acid and base that are coming together, so then the dissociation of the constant is going to be related to the dissociation of the conjugate base. Okay, and so we basically are going to get Ka times Kb is going to give us our K water. So if we actually do that, let's go back. Oops. And so instead of using A, we're going to use A for our thing down here. So we're going to have HA. These guys are going to cancel out when you multiply them. These guys are going to cancel out when you multiply them. And so then you're just left with KW. Does that make sense? So if we take into consideration that conjugate acid and the conjugate base, then we just get Kw. Okay. Question. Okay, so there are like tons of for tables of weak acids and things like that. There are tons of dissociation constants that are used, but these are also called acid-base dissociation constants. So how do we use it?
They would be in
go
the
ahead.
book.
What was that?
I'm assuming they would be in the book.
Yeah, they're usually, there's a table in the back book.
Okay.
They'll be given to you on the exam, unless I get really old and forget, you know, which does happen quite a bit lately these days. Calculate the Ka for dissociation of 0.100 molar of hypochlorous acid solution with an equilibrium hydrogen ion concentration of 2.34 times 10 to the minus 5. So we're trying to calculate Ka. And so we know that the Ka is going to be equal to concentration. Oops. What does hypochlorous acid look like? Or chlorous acid? Anyone? You guys remember that? HClO?
No, honestly, I was gonna look up on my polyatomic ions because I knew it was just one less oxygen.
It's 2
Did you
less,
add
right?
that?
Than or 8. Yeah. So chlorate is ClO3. Chlorite is ClO2, and then hypochlorite is ClO. Okay.
Mhm.
How will we calculate this?
Would you?
Do you do anything with the molecular weight?
Do we
Just-
need to do anything with molecular weight? Because we have the
I think-
concentration. We have the concentration of this guy, right? We have the starting concentration. So if we did ice tables for this reaction, right? So ICE, this guy's starting out at 0.1. The change is going to be, quote, X. And so this guy's going to be minus X. So then this guy's going to be 0.1 minus X. So we know what X is. X is going to equal, because they give it to us, 2.38 times 10 to the minus 5. I don't know why I use X when I know I have to do that. Molar. And that's a 5, not 3. Okay, so then we just subtract that value, 0.100 minus 2.38 times 10 to the minus 5. You're going to get a really, really small number that isn't going to change too much, or you're going to basically get this number that's not going to change too much. So we'll basically get 0.11. If we go 3 sig figs, we know that these guys are going to be the same. So then it's just going to be 2.38 times 10 to the minus 5 squared. Oops.
See, I was gonna say that you were just gonna divide the two, but I wasn't sure if that was right.
Yeah. So then Ka is going to equal so Ka is going to equal the 5.66 times 10 to the minus 9. Okay. Piece of cake?
Yeah.
Good. Okay, so we're going to stop here. We'll pick it back up on Monday.
I did have a question about lab 6.
Okay.
It says on the direction or the procedure for the boiling point curve will be generated using computer interface temperature probes.
Yeah.
We did not do that in the lab.
Okay, so then just use the manual boiling point temperature.
Okay, I was about to say we just used the regular thermometer.
Yeah, which is, it kind of worked out for you guys because they had a lot of trouble with the boiling point or the temperature probes. Tons of issues with that.
The lab also mentions that the computer program is going to like generate a graph for you. What type of graph do we need to like make that in Excel or what?
Yeah, so you guys would make it in Excel.
What type of graph would it be?
So because you're looking at the different boiling points, you should actually get a scatter plot graph.
Wait, I'm sorry.
Scatter plot.
Oh, scatter plot. Okay.
Yep.
And what is it? What is it going to be? Is it going to be like time versus temperature, or?
Yes. So you should have one that's time versus.
Okay. With the time.
Yep. And then you should also have one that is time versus concentration, right? Because then you have different concentration of, not time versus concentration, temperature versus concentration, right?
Yeah, because we had different amounts of the salt.
That's right.
I also wanted to ask, I think it was lab 8, but I might be misremembering the number. but it was the one that we didn't do anything for because it ended up not working. There's like a place to upload, but I'm not sure what exactly we're supposed to do.
You guys are just basically just remind me that it did not work, you know?
Okay.
So
Okay.
yeah, so you guys weren't able to collect any data because that one didn't work. And then that reminds me, I've ordered new chemicals, but we'll see for that one, you know.
And my last question for lab 6 was, it says graph the data and use graph to determine the KB of water. And I know the equation for that you gave us to determine the temperature of the boiling point is delta T equals mkb. So is it a true statement if KB equals delta T over M, molality? So that's how you would figure out KB?
That's right.
Okay. Because I've been getting really, like, I've been doing it like that, but I've been getting like high numbers for KB, and I don't know if it's like right.
So you got to remember, it represents delta T represents temperature change in temperature, right?
You cut out, sorry.
So that delta T represents change in temperature.
Yeah. So
Okay.
what I did was like, if I labeled my boiling point at 70 degrees, I just did 70 minus 20 because of room temperature, right?
No. So that would be your delta T. It should be what water normally boils at.
Oh, so it would be 100.
Yes.
Oh, that's what I've been doing wrong then. Okay. So it'd be like 100 minus 70 or something.
That's right.
Okay.
Any other questions?
Are we gonna do a lab today, or are we just gonna?
Yeah, we're going to be picking up where we left off. And next week, you guys are going to have one more lab. It is going to be electron, what is it? Voltage lab. You're going to have a voltage lab next week. I just have to finish ironing out the last part of the details. I made changes to it. Hopefully it works. Knock on wood. So. So you're going to be using your LEDs next week. You're going to be using the metals. Do you guys have the metals in your kits?
I would have to look, but I think so.
Okay. Anybody who may be missing the metal, let me know, and I'll deliver.
Also, Dr. Henry, I have not seen the little, I don't remember what you said it was called, the thing for the wine that's supposed to bob. I've not seen it move once yet. I'm concerned.
Really?
Yeah.
Okay, so that's what we're gonna do today in lab. So let's go to the lab because there are going to be a few people that are going to be joining us.
Okay.
Late. So let's go to the lab and I'll see you guys